Hey, and welcome to Teach Me in 10, the video series brought to you by Technology Networks. Here we invite scientists to describe their research area in less than 10 minutes. My name is Rihanna Lilly and I'm an editorial assistant for Technology Networks. Our guest today is Amos Fumagalli, a postdoctoral researcher at the Netherlands Cancer Institute. Today, Amos is going to teach us about the basic principles of Western blotting, including its strengths and weaknesses.
Hello, everyone. Thank you very much for this kind introduction, and thank you very much for having me here in this amazing series of Teach Me in 10, where I'm going to introduce you to the basic principle of one of, if not the most used technique in any biochemical and biological lab. Because I'm confident that if you're working in such a lab, in the past you have used, probably you are using right now, but 100% sure you are going to use the Western blotting, because in my experience, the last Western blot does not exist. What is Western blotting? Western blotting is the technique that allows us to transfer the protein from a gel to the membrane, allowing us then to detect it and quantify it. I just discovered for this presentation that Western blotting, the name, came from the fact that this technique is very similar to the Southern blotting, and one of the scientists that discovered this technique was working on the West Coast. So that's why Western blotting. Despite being really much still used, this technique is not so recent, has been discovered in the 1980s. And from that moment, the basic principle of these techniques have not changed. For the purpose of this presentation, I divided these techniques in 5 steps. I want to clarify also that I will focus on the 1D Western blotting done on denaturated protein because it's the main area of my expertise. It's the technique that I use the most. For this technique, the first step is the preparation of the sample. So you have your cells, tissue, or any matrix containing your protein. What you need to do is that you need to denaturate it. So disrupting the secondary and tertiary structure of the protein, making it linear, using heat, using any detergent. After your protein is linearized, what you have to do is that you need to negatively charge it using SDS. This SDS charge it, but also charge in a way that the charge are directly proportional to the length, to the size of the protein. Once you have your linearized and negatively charged protein, what you do is that you put them in those wells of a polyacrylamide samples, and then you apply a current. Your protein are negatively charged, so they will migrate towards the positive charge inside this gel. This gel, you can consider it as a strainer because it's done in a way that a mesh is formed. In this way, the smaller protein can migrate through this net very easily, arriving to the bottom of the gel, whereas the bigger protein will remain stuck on the top part. So you will separate the protein based on their size. As you can see here, I put ladder because in the first well, what you do is that you put a commercially available mixture of protein with a well-defined molecular weight that you will use as a reference in order to check what is the molecular weight of your target protein. After you separate the protein by size, what you have to do is that you need to do the actual blotting. So for this blotting, you apply again a current. Your protein will migrate from the negatively charged to the positively charged and will migrate from the gel to the membrane. So then you have your protein on the membrane. What you have to do is that you need to block them using a source of protein. Usually it's BSA or powder milk in order to block all the specific binding sites. And then using an antibody, you are going to detect the protein of interest. So 5 steps, quite easy, but each one of these steps is critical for the success of the technique. In my experience, what I found is also that each of these steps is surrounded by tradition in each lab. What I mean by that is that you go into a lab, they will tell you to migrate your protein in a slow fashion. In another lab, they will tell you to migrate fast. In one lab, they will tell you that overnight transfer is better. In another one, that you need to do 2 hours. In one lab, they prefer the liquid transfer. In another lab, the semi-dry transfer, and so forth, so on. The advice they can tell you is that you need to try to adapt to what the lab is using, try to use the technique and the refined technique that you are using, unless it's something completely wrong. So then you speak up and you say it. So as I told you, this technique is quite used, but what are the weaknesses, at least in my point of view? The first weakness is that this technique is not suitable for large screen, is quite low throughput, because of course in a gel you can charge only a limited number of samples between 15 and 20. You don't want to find yourself in a lab with more than 3, 4, 5 membranes, because first, can be quite messy, and secondly, because you will need to use a large amount of antibodies, so quite costly. Instead, if you do sequentially one after the other, you can reuse the antibody. So not a lot of samples, and also inside the same membrane, you cannot test an infinite number of protein. Usually, if you're lucky, you can arrive at 6, 7 protein, but more start to be challenging. In order to overcome this issue, in the past years, new tools have been invented, like the use of secondary of antibody coupled to fluorescence that can allow the detection of several proteins simultaneously. Then the second, and for me, the biggest weakness of this technique is the fact that it completely relies on the use of an antibody. That it's very good if you have a very good antibody against your protein, but it's not so good, of course, if you don't have a good antibody, because maybe the antibody does not exist, and you cannot use this protein unless you insert some tags, or your antibody exists, but it's not so specific. So you have multiple bonds in your gel, and then it starts to be tricky to identify the good one. A tool that helped me really a lot to choose the best antibody commercially available for the protein that you want is this one, is BenchSci, because it's a website where you can put the name of your target protein, and then they will give you all the commercially available antibody with the reference, with the figure also of the Western blotting. So you don't have to spend any more time on PubMed. That can be quite time consuming. And the third weakness for me of this method is that it can be challenging sometimes to see different expression level between conditions. So if you have a qualitative study, presence or absence of big difference, it's super easy. But if you need to know the difference, a small difference can be quite challenging, especially because traditionally, okay, as I told you, we need to quantify the protein of interest. You visualize it, you see it, but then you need to compare with the reference protein. Traditionally, this reference protein will be used like a housekeeping protein, such as actin, tubulin, and other proteins that we think do not change so much between one condition and the other. But in my opinion, what really helped me to do this small quantification is that to use total protein as a reference. So you stain for total protein, and you can do that using commercially available kits that are super nice, usually based on fluorescence, but you can also do in the old-fashioned way using Ponceau red if you wish. So these are the weaknesses, but this technique, as I told you, is very much used because it has also a lot of strengths. The first strength is its simplicity. As I told you, 5 steps, quite easy. After less than 1 week, everyone can do it in the lab. But of course, to master and to troubleshoot can be quite challenging. I'm still learning, and I see sometimes weird stuff that I cannot explain by Western blotting. The second is the low cost. The equipment is quite inexpensive. The only thing expensive is the antibody. But if you have a good antibody, you can blot really for a long time with this antibody. It's still considered a golden standard for protein identification. If you do mass spectrometry, for example, it happens to me in the past, you do mass spectrometry, you identify a differential express protein, they anyway ask for Western blot to confirm it. And it's very robust. So if your results is there, if your results are, if your difference is there, doesn't matter how you run it or what you do, you will see this difference. So I hope you enjoyed this presentation on the basic principle of Western blot. If you have any issue for Western blot, you want to contact me, I leave there my working email. You can find me also on LinkedIn if you want. And with that, I will thank you very much for your attention, for this opportunity, and I wish you a happy blotting. Thank you very much. Bye-bye.
Thank you for joining us here today at Teach Me in 10. If you'd like to learn more about Western blotting or Dr. Amos Fumagalli's work, make sure you check out the resources linked in the video description below. Stay tuned for the next installment of Teach Me in 10. Bye!